dear students, in the previous class we had seen writing the polynomials in 1 dimension, 2 dimensions and 3 dimensions. One can write the polynomials in 2 dimensions with the help of a Pascal's triangle. We can also write the polynomial in 3 dimensions with the help of tetrahedron. Okay? Now we shall see the shape functions using polynomials. The shape functions using polynomials. We know that the polynomials are used for shape functions. Initially, they were derived in terms of Cartesian coordinates. Later, the natural coordinates were identified and the advantages were noticed. So therefore, the researchers began deriving the shape functions in terms of natural coordinates. Okay? Now we shall see the polynomial functions in terms of Cartesian coordinates. In this approach, we take the number of constants appearing in the polynomial equal to the number of degrees of freedom in the element. In this approach, when we write a polynomial for shape function, the number of constants appearing in the polynomial must be equal to the number of degrees of freedom of the element. Okay. Now, care must be taken to see that the geometric isotropy is not lost. Care must be taken to see that the geometric isotropy is not lost. Using nodal values, the number of equations equal to number of constants in the polynomial is formed and then the constants are determined. Using the nodal values, the number of equations equals to the number of constants in the polynomial is formed and then the constants are determined. Then the shape functions are identified. Okay, this procedure may be called as generalized coordinate approach. This procedure is called as generalized coordinate approach. Since the constants in the polynomial are called as generalized coordinates. Generalized coordinates. Okay, so now we derive the shape functions for two-noded bar or truss element. We derive the shape functions for two-noded bar or truss element. Now visualize this diagram. We have a one-dimensional element which connects two nodes 1 and 2. This element is used for finite element modeling of one-dimensional problems. Okay? Example is axially loaded bar. Axially loaded bar. The bar may undergo compression or tension. The bar may undergo compression or tension. Right? A bar of uniform cross section carrying a pull is the example for axially loaded bar. A bar of uniform cross section supporting a push is the example for axially loaded bar. Okay? For one-dimensional problems, we use one-dimensional element connecting two nodes. So here, each node has 1 degree of freedom. Each node has 1 degree of freedom. Now this is node 1 which has 1 degree of freedom like this, which is U1. This node 2 has another degree of freedom which is U. Okay. Now this is the reference frame. Okay. The reference frame has one coordinate axis x. Where is the origin? Here. This is the origin. Okay. Now node 1 is identified by the coordinate x1. Now node 2 is identified by the coordinate x2. Node 1 is specified by the coordinate x1. Node 2 is specified by the coordinate x2. Then, what is the length of the element? x2 minus x1. Okay. Say, P is the point of interest. Now, my interest is to determine the displacement of this point P. What is this displacement? Say U. Okay. So now, I want to derive the shape functions for this element in global coordinate x. Okay. Therefore, how can I write the displacement function? How can I write the equation for this, displacement U? I can use a polynomial. How many constants can I consider in this polynomial? This question comes into mind. Okay. Here the condition is, as I said, the number of constants appearing in the polynomial must be equal to the number of degrees of freedom in the element. How many degrees of freedom are there? There are 2 degrees of freedom. Therefore, when I write a polynomial for displacement function, right, the polynomial must contain same number of constants. Simply we can say, when we write a polynomial for displacement, number of constants appearing in the polynomial equals to the number of degrees of freedom in the element. Because there are 2 degrees of freedom, I take 2 constants. Then what is my polynomial? U equals to alpha 1 plus alpha 2x. Or you can write like this. Say U equals to A plus bx. Okay? Where A and B are the generalized coordinates. Okay? So here, in this equation, alpha 1 and alpha 2 are the generalized coordinates. What approach we are following? Generalized coordinate approach. Okay? Now, what is our interest to determine alpha 1 and alpha 2? Then we have to substitute in this equation. Then we get an expression for the displacement U. Okay? From which, we obtain the shape functions. That we see now. Okay. We have the expression U equal to alpha 1 plus alpha 2 into x. That we write in matrix form. How you write? U equals to a row matrix having the elements 1 and x into a column matrix having the elements alpha 1 and alpha. Okay? Right. Now, we have determined alpha 1 and alpha. Okay? Therefore, a column matrix, having the elements alpha 1 and alpha 2 is to be determined. So, how you do? Now, what you do is, you come back and see this diagram. At x equals to x1, u equals to u1. What is u here? Displacement of the point of interest. At x equal to x1, u equals to u1. This is one condition. This is one condition. At x equal to x1, u equals to u1. This is one condition. I can write here. At x equal to x1, u equals to u1. This is one condition. Next one. At x equal to x2, u equals to u2. This is another condition. Because there are 2 generalized coordinates appearing in the polynomial, these unknown generalized coordinates we can determine from these 2 conditions. Okay? Because there are 2 unknowns, you want 2 equations. Right? That we write now. How? Take the first condition. At x equal to x1, u equal to u1. Therefore, I write u1 equals to alpha 1 plus alpha 2 into x1. Next one. At x equal to x2, u equals to u2. Therefore, now u2 equals to alpha 1 plus alpha 2 into x2. We have two equations. What are u1 and u2? They are the nodal displacements. They are the nodal displacements. Okay? u1 is the displacement of node 1 and u2 is the displacement of node 2. Now these two equations we can write in matrix form. Okay? Right. Now, come here. We have the expression here. What is first one? u1 equals to alpha 1 plus alpha 2 into x1. And what is second one? u2 equals to alpha 1 plus alpha 2 into x2. We have these two equations. These we can write in matrix form. Right? How? Like this. See here. A column matrix having the elements u1 and u2 which equals to. Okay? Now, a 2 by 2 matrix into a column matrix having the elements alpha 1 and alpha 2. Now, what are the elements of this? Take this expression, this equation, u1 equals to alpha 1 plus alpha 2 into x1. Therefore, we write 1 here, 1 into alpha 1 plus x1 into alpha. Similar, u2 equals to alpha 1 plus alpha 2 into x2. Hence, I can write 1 here and here I write x2. Okay. These two equations are represented in matrix form. This is how I have written here. A column matrix having the elements u1 and u2 equals to a 2 by 2 matrix having the elements 1, x1, 1, x2 into a column matrix having the elements alpha 1 and alpha. Now what is my interest? My interest is to determine here alpha 1 and alpha 2. This I want because they are unknowns. Once I determine alpha and alpha 2, I can substitute here. Then I get the expression for the displacement at the point of interest P. Okay? Now, what are u1 and u2? They are the nodal values. Okay? Now, a column matrix having the elements alpha 1 and alpha 2 here equals to, now, inverse of this matrix that we write here into a column matrix having the elements u1 and u2. Okay. A column matrix having the elements alpha 1 and alpha 2 equals to inverse of this matrix into this matrix. That is what I have written here. Okay. Which equals to, now inverse of this. How we get? 1 by x2 minus x1 into a 2 by 2 matrix x2 minus 1 minus x1 1 transpose. Understand? Into again a column matrix with elements u1, u2. I hope you understand this. I hope you understand this. Inverse of this matrix is this. Okay? 1 by x2 minus x1 into transpose of a 2 by 2 matrix having the elements x2 minus 1 minus x1 1 into again a column matrix having the elements u1 and u2 again, which equals to 1 by, what is x2 minus x1? It is the length of the element. Therefore 1 by L into transpose of this matrix. Okay? When you take transpose of this, row becomes column. Okay? What is the row? What is the first row? The first row is having the elements x2 and minus 1. Now this row becomes column x2 minus 1. then this row becomes column minus x1 into again a column matrix having the elements u1 and u2. Understand? Now, alpha 1, alpha 2 we have. So what is alpha 1? Alpha 1 is 1 by L into x2 u1 minus x1 u2. That is what we understand. Okay? And alpha 2, what is alpha 2? 1 by L into minus u1 plus u. Understand? Right. Now, come back here. U equals to a row matrix having the elements 1 and x into a column matrix having the elements alpha 1 and alpha. This equals to, again, same row matrix we write here into, now in place of this column matrix, what you write? You can write this. That is 1 by L into a 2 by 2 matrix, having x2 minus x1 minus 1, 1 into a column matrix with elements u1, u2. Now, the displacement u equals to, right, 1 by L, right, into, now multiply these two matrices. Multiply these two matrices. What is the size of this matrix? 1 by 2. And what is the size of this matrix? 2 by 2. Therefore, the resultant of these two you get, a matrix of size 1 by 2, simply a row matrix. Okay. So now, so how you get? So here, 1 into x2, right, plus x into minus 1. Therefore, you get x2 minus x. Next, 1 into minus x1 plus x into 1. Therefore, you get minus x1 plus x. Right? This is one element and this is another. Into a column matrix having the elements u1 and u2. Okay? Right. So now, if you take this 1 by L inside, then what you get? x2 minus x by L, that is one element. And another element is minus x1 plus x by L. Therefore, what is the expression for the displacement u? The expression for the displacement u is equal to a row matrix having the elements x2 minus x by L, x minus x1 by L into a column matrix having the elements u1 and u2. Okay, this is one element. This is another element. If you multiply these two, then what you get? You get like this. Again, say u equal to x2 minus x by L into u1 plus x minus x1 by L into u2. You get like this, x2 minus x by L into u1 plus again x minus x1 by L into u2. This is how you get. Clear? Now, what I do is, I assume like this. Displacement u equals to, say n1 into u1. What is n1 here? I say n1 is simply x2 minus x by L. This I say n1. n1 plus, now, n2 into u2. This is u2. What is n2 here? X minus x1 by L. This bracketed term I say n1. and this bracketed term I say n2. Then how you get the displacement function u? Then you get u equals to n1 u1 plus n2 u2, where n1 and n2 are known as shape functions, which are derived in terms of the global coordinate x, in terms of the rectangular coordinate x, in terms of the Cartesian coordinate x, where n1 and n2 are known as shape functions. What are shape functions? Approximating functions or interpolating functions. What is n1? x2 minus x by L. What is n2? x minus x1 by L. Okay. Now what is u? It is the unknown displacement. It is the unknown displacement at the point of interest. What is u1? It is the displacement of node 1. What is u2? It is the displacement of node 2. What are n1 and n2? They are the shape functions derived in terms of the coordinate x. That is what we see here. n1 equals to x2 minus x by L and n2 equals to x minus x1 by L. Okay. Now here, this function represents a linear polynomial. This also represents a linear polynomial. Hence we say, these are the linear shape functions. Okay. Now, see here, x is variable. Therefore, how each shape function varies with respect to length of the element. That we see here. Now, this is an element connecting two nodes, 1 and 2. What is the length of the element? L. Okay. Now, we know that node 1 is specified by the coordinate x1 and node 2 is specified by the coordinate x2. Therefore, at x equal to x1, that is at node 1. Now, at x equal to x1, in place of x, put x1. At x equal to x1, that is at node 1. So, in place of x, put x1. Then, n1 equals to x2 minus x1 by L. What is x2 minus x1? L. Hence, n1 equals to L by L. You get 1 unit. Right? Next, at node 2, that is, at x equal to x2, what is the value of the shape function n1? That we see. At x equal to x2, then what happens? n1 equals to x2 minus x2 by L 0. Therefore, we have the shape function n1 0. Because this is a linear function, hence you get a straight line. The variation you get linearly like this along the straight. Okay. We know that shape functions represent dimensionless numbers. Therefore, n1 equals to x2 minus x by L. It has no dimension. Similarly, n2 also, it has no dimension. Okay. Next, we see how n2 varies with respect to length of the element. At node 1, x equals to x1. Therefore, take the second function. Put at x equal to x1, then n2 equals to 0. Yes. Okay. Next, at node 2, that is at x equal to x2, then at x equal to x2, x2 minus x1 equals to L. Therefore, n2 equals to 1 at node 2. And how n2 varies with respect to length L? Linearly, because this represents a linear polynomial which is in the form of, say, y equals to mx plus c. This also. Hence you get a straight line like this. Okay. We know that at each point on the element, sum of the shape functions is unity. Okay. Where n1 and n2 are the shape functions. At node 1, what is n1? Unity. What is n2? 0. Therefore, n1 plus n2 equals to 1. At node 2, what is n2? 1. And n1 0. Therefore, at node 2 also, n1 plus n2 equal to 1 is satisfied. Not only at the nodes, at any point on the element, if you sum up both shape functions, their summation equals to 1. Okay? Do you understand how we have derived the shape functions in terms of the Cartesian coordinate x? N1 equals to x2 minus x by L and N2 equals to x minus x1. You have to remember. Shape functions in Cartesian coordinate x. Now we shall see the shape functions in terms of natural coordinates. Natural coordinates. Shape functions can be derived easily using polynomials in natural coordinates. Shape functions can be derived using polynomials in natural coordinates. This approach makes it possible to find the shape functions for more elements. Therefore, few cases we see now. The first case is deriving shape functions for two-noded bar element using natural coordinates. We have a diagram here. Visualize this. We have a two-noded bar element. As I said, each node consists of how many degrees of freedom? 1 degree of freedom. Node 1 has the degree of freedom u1 and node 2 also has the degree of freedom u2. Right? Remember, they are the displacements. Okay. Now P is the point of interest. It is specified by two natural coordinates L1 and L2. Right? We know that at node 1, L1 is 0 and L2 is unit. L1 is 0 and L2 is unit. Okay. And at node 2, L2 is unity and L1 is 0. Make correction. At node 1, L1 is unity and L2 is 0. At node 2, L2 is unity and L1 is 0. At node 1, L1 is unity, L2 is 0. At node 2, L1 is 0, L2 is unit. Okay. So now, so how you write the function for the displacement u equals to, say, alpha 1 into L1 plus alpha 2 into L2. Remember, sum of the natural coordinates L1 and L2 equals to 1. We know this kind. Now u equals to alpha 1 L1 plus alpha 2 into L2. Okay. So how you write this? In matrix form, a row matrix having the elements L1 and L2 into a column matrix having the elements alpha 1 and alpha. Okay. Now, at node 1, u equals to u1. At same node, L1 equals to 1 and L2 equals to 0. That is what we have seen. At node 1, L1 is equal to 1 and L2 is equal to 0. Okay. What is the displacement of node 1? u1. We impose these conditions. At node 1, u equals to u1. At same node, L1 equals to 1 and L2 equals to 0. Next, at node 2, U equals to U2. Therefore, L1 equals to 0 and L2 equals to 1. These conditions we apply. That we see now. Okay. Why we apply these conditions? Because we have two unknowns here, alpha 1 and alpha 2. We have to determine. Therefore, we apply these two conditions. What is first condition? At node 1, U equals to U1. L1 equals to 1 and L2 equals to 0. This is first condition. And what is second condition? U equals to U2 at node 2, and for which L1 equals to 0 and L2 equals to 1. This is second condition. We have two unknown, therefore we want two conditions. What for? To acquire two equations. That we see. At node 1, U equals to U1. Therefore, U1 equals to 1. Okay? Now, L1 equals to 1. Right? You get alpha 1 plus L2 equals to 0. Okay? So, plus 0. Understand? So, therefore, what you get? Alpha 1. Second condition. At node 2, U equals to U2. Therefore, U2 equals to. L1 is 0. So, therefore, 0 plus. And L2 equal to 1. Alpha. This equals to alpha. We have two equations. These two we represent in matrix form. A column matrix having the elements U1 and U2 equals to a column matrix having the elements U1 and U2, which equals to a 2 by 2 matrix into a column matrix having the elements alpha 1 and alpha 2. U1 equals to alpha 1, therefore 1 we put here 0 here. 1 into alpha 1 plus 0 into alpha. Next, U2 equals to alpha 2, therefore we put 0 here, we put 1. 0 into alpha 1 plus 1 into alpha 2, alpha 2. This is how I have written here. A column matrix having the elements U1 and U2 equals to a 2 by 2 matrix having the elements 1, 0, 0, 1 into a column matrix having the elements alpha 1 and alpha 2. Okay? Now, what is our interest? We determine alpha 1 and alpha 2. Once you determine alpha and alpha 2, you can substitute here. Therefore, alpha 1 alpha equals to inverse of this matrix. Inverse of this matrix. We have written here. Into a column matrix having the elements U1 and U2. Inverse of this matrix remains same. Okay? Remains same, you get same into a column matrix having the elements U1 and U2. Okay? Now, U equals to, again come here, a row matrix having the elements L1 and L2 into a column matrix having the elements alpha and alpha. Hence, U equals to a row matrix having L1 and L2 equals to, in place of this column matrix, what you can write? This you can write. A 2 by 2 matrix having the elements 1, 0, 0, 1 into a column matrix having the elements U1 and U2. This equals to, again, a row matrix having the elements L1 and L2 into, now multiply these two. The size of this is 2 by 2. Size of this is 2 by 1. You get ultimately a 2 by 1 matrix. Okay? When you multiply these two, 1 into U1 plus 0 into U2, you get U1. 0 into U1 plus 1 into U2, you get a 2 by 1 matrix. Now, the displacement U equals to a row matrix having the elements L1 and L2 into a column column matrix having the elements U1 and U2. So what is the general form for the displacement? The general form for the displacement field U equals to, right, the shape function, the first shape function N1 into U1 plus the shape function N2 into U2. This is the general form for the displacement. The displacement field is represented in general like this. What are U1 and U2? They are the nodal displacements. What are N1 and N2? They are the shape functions. Therefore, if you compare this form, right, with this, how we get U equals to L1 U1, U equals to L1 U1 plus L2 U2. When you multiply these two, you get like this. So compare this form with this. Then N1 equals to L1. N1 equals to L1. Then N2 equals to L2. What you understand from this? We can understand that the natural coordinates L1 and L2 will appear as the shape functions. The natural coordinates L1 and L2 will appear as the shape functions. That is what we can understand from this discussion. Okay. Another case. Shape functions for a two-noded bar element taking natural coordinate J. It is a Greek letter. Okay. Now, visualize this diagram. We have a one-dimensional element connecting two nodes. Okay. Length of this element is covered as J varies from -1 to +1. -1 to +1. Length of this element is covered as J varies from -1 to +1. That is what we learned in one of the classes. Right? So now, here, this is first node, this is second. Okay. So how you choose the displacement function? We choose the displacement function as the polynomial containing the coordinate J with the number of constants equal to number of degrees of freedom of the element. How many degrees of freedom are there in the element? There are 2 degrees of freedom. 1 degree of freedom at node 1 and another degree of freedom at node 2. Therefore, there are 2 degrees of freedom. We take the displacement function as a polynomial in coordinate J with same number of constants. There are 2 degrees of freedom, hence we take 2 constants in the polynomial. So how we write? Hence U equals to alpha 1 plus alpha 2 into J, where alpha 1 and alpha 2 are the generalized coordinates which we have to determine and substitute in this, from which we obtain the shape functions. Okay. Now this equation is expressed like this in matrix form. How? U equals to a row matrix having elements 1 and J into a column matrix having the elements alpha 1 and alpha. Okay? So now, a column matrix having the elements alpha 1 and alpha 2 we have to determine. How you determine, that is the question, right? This is the reason why, again, we visualize this diagram. At node 1, what is the displacement? U1. And at node 2, what is the displacement? U2. Okay. Now, we can write the conditions like this. At At node 1, u equals to u1. At the same node, what is j? J equals to minus 1. This is the condition. Right? And at node 2, okay, u equals to u2. And for the same node, j equals to plus 1. There are two conditions. These two conditions we use to determine two unknowns, alpha 1 and alpha. With these two conditions, we write two equations. How? That we try now. At node 1, u equals to u1 and j equals to minus 1. Therefore, u equals to u1. u1 equals to alpha 1 minus alpha 2 because j equals to minus 1. And next one. At node 2, u equals to u2 which equals to alpha 1 plus alpha 2 into 1. Therefore, you get 1. Now, can you express this in matrix form? Yes. A column matrix having the elements u1 and u2 which equals to a 2 by 2 matrix having the elements 1, minus 1, 1, 1 into a column matrix having the elements alpha 1 and alpha 2. This is how we can write. Okay? That is what we have seen here. Right? Now what we want? Alpha 1 and alpha. Alpha 1 and alpha 2. This we want. Now column matrix having the elements alpha 1 and alpha 2 equals to transpose of this matrix. Inverse of this matrix. Okay? Inverse of this matrix into a column matrix having the elements u1 and u2. Okay? Now, a column matrix having the elements alpha 1 and alpha 2 equals to inverse of this you can try. Okay? Inverse of this you can try. How you write? Inverse of this. It equals to 1 by. Okay. I write a formula. If we have a matrix with elements A, B, C and D, how you get inverse of this? I say this is the matrix A. How you get inverse of this? Now, inverse of this matrix equals to 1 by AD minus BC into a 2 by 2 matrix having the elements D minus B minus C A. We use this formula. Now, inverse of this matrix we want. How do you get 1 by 1 into 1, 1 minus of minus 1, that is plus 1 into again a 2 by 2 matrix having the elements, and according to this 1, 1 and here plus 1, here minus 1. 1 by 2 into a 2 by 2 matrix having the elements 1, 1 minus 1. That is what we have here. That is what we have here. Into a column matrix having the elements u1 and u2. Okay? So now, so what we do? Again, we go back to the, previous equation. That is, u equals to a row matrix having the elements 1 and j into a column matrix with the elements alpha 1 and alpha. Right? Same expression we take. Same expression we take. So u equals a row matrix having the elements 1 and j into a column matrix having the elements alpha 1 and alpha. This equals to a row matrix having the elements 1 and j into, in place of this, what you have to do? You have to substitute this. So 1 by 2 into a 2 by 2 matrix having the elements 1, 1, minus 1, 1 into a column matrix having the elements u1 and u2. Okay. Again, u equals to 1 by 2 into, now this is a row matrix of size 1 by 2. This is a 2 by 2 matrix. Now multiply these two. Okay. When you multiply these two, how you get? You see here, 1 into 1 plus j into minus 1. 1 minus j. Okay. Next, 1 into 1 plus j into 1. 1 plus j. 1 minus j, this is one element. 1 plus j, this is another element. Okay. We have a row matrix. When you multiply these two, you get a row matrix with elements 1 minus j and 1 plus j into, again, column matrix having the elements u1 and u, as it is. Okay, now take this 1 by 2 inside. Then what you get? 1 minus j by 2. Next one, 1 plus j by 2 into a column matrix having the elements u1 and u. What is the general form for the displacement function? The general form for the displacement function u equals to n1 u1 plus n2 u2. Okay? Therefore, so what I do is, so here I take u equal to 1 minus j by 2, 1 plus j by 2, right, into a column matrix u1 u. This 1 minus j by 2, I say n1. 1 minus j by 2, 1 minus j by 2, I say n1. 1 plus j by 2, I say n2. Therefore, a row matrix having elements n1 and n2 into a column matrix with elements u1 and u. Okay? Now, do we have, a form like this? Yes. That is the reason, right? The obtained expression, if you compare with this form, you get n1 equals to 1 minus j by 2. n1 equals to 1 minus j by 2 and n2 equals to 1 plus j by 2. What are n1 and n2? They are the shape functions. Right? The shape functions n1 and n2 are defined in terms of the natural coordinate j. They represent linear polynomials. Linear polynomials. Now you see how they vary with respect to length of the element. You have here n1 equals to 1 minus j by 2 and n2 equals to 1 plus j. And how they vary with respect to length of the element. So this is the element having 2 nodes. L is the length of the element. At node 1, you know that j equal to minus 1 at node. Therefore, in this expression, put j equal to minus 1. Then n1, how much you get? 1. n1 is at node 1. Right? At node 2, j equals to plus 1. Therefore, put 1 here in place of j. Then n1 equals to 0. We have n1 here. At node. How n1 is varying? Linearly, because this represents a linear function. This represents a linear polynomial in coordinate j, in natural coordinate j. Okay, right. Now we take the other shape function n2. At node 1, j equals to minus 1. Hence, put j equal to minus 1. Then you get n2 equals to 0 at node 1. Next, put j equal to plus 1. Then you get n2 equals to 1. How it is varying? Linearly. Okay? Because now this n2 represents a linear polynomial in coordinate j. Okay? Understand? Now, what is the sum of the shape functions at each point on the element? Unity. The sum of the shape functions, we know that sum of the shape functions is unity. At node 1 and at node 1, n1 is unity, n1 is 0. Therefore, n1 plus n2 equals to 1. At node 2, n1 is 0 and n2 is unity. Therefore, n1 plus n2 equals to 1 at node. At any point on the element, if you determine the sum of the shape functions, it is unity. For example, I take the midpoint of the element. This is the midpoint. At midpoint, j equals to 0. J equals to 0. Right? Now, put j equal to 0 here. Then n1 how much you get? 1 by. And n2 how much you get? 1 by. If you sum up both shape functions, you get unity. n1 plus n2 equals to 4. Okay? These are the shape functions for one-dimensional problems in natural coordinate j. Okay. Thank you very much.